So hello everybody and welcome back to another video by Funlearn Tutorials. So we are going to be continuing from where we left off last time. What we are trying to find out is an iterative process for AR1, which gives us an alternative perspective of what the story reveals when we look at an AR1 DGP series. And we have also discussed about the brief ideas about what an ARP process actually is. ARP process, right? So essentially this is what we have when we put t equal to 3. I suggest you have a brief look at what we have done as of yet. The videos will be linked up in the top right corner of this current screen as well as in the description box below for this particular YouTube video. We have already tried t equal to 3 and what we're going to do is right now we are going to use an induction or an intuition of sorts. Of course, we are not going to keep using t equal to 4, t equal to 5, but rather we are going to be looking at the expression that we have currently and we are going to be deducing what we can have if we put maybe t equal to k. Right, so what do we have if we put t equal to k? So we have yk on this side because the original expression was y1, right? So because yt, you put t equal to 1, you get y1, you put t equal to 2, you get y2. So put t equal to k, you get yt. Now let's keep this on the screen. So you have phi naught, right? This expression says we can get a phi naught here. Then when we had t equal to 3, it went up to 1 plus phi 1 plus phi 1, 2. It went up to 2. When we had 3, it went up to 2. So what we can, even here, if we had taken phi naught common, we would have 1 plus phi 1. So for t equal to 2, it would have gone up to phi 1. For t equal to 3, it's going up to phi 2. So we can safely deduce that for yk, that is for t equal to k, it will go up to phi naught into 1 plus phi 1 plus phi 1 square. It will go up to phi 1 3, so on and so forth, up to phi 1. So we have phi 1 k minus 1. See, you have 3 and it goes up to 2. You have 2, it goes up to 1. So if it's k, it will go up to k minus 1, just one period lag. This is for this part. So this is this part. Then you have this term. I didn't highlight it properly. Yeah. Okay, why isn't it highlighting? Yeah. So then you have this term. See, for t equal to 3, you have phi 1 cube y naught. For t equal to 2, you have phi 1 square y naught. So that means for t equal to k, you have something like plus phi 1 to the power k y naught, right? You have this term. It's corresponding to the expression that we had found out earlier. So this term, let me just change the color, this term boils down to this term when we generalize t equal to k. Then we have this third term, right? So we have this third term, and what we see, it starts from the highest number, right? So it let's say how we can express that, or we can express it in the reverse way. So we have y3 epsilon 3. So it's going to be starting from epsilon k, right? It's going to start from epsilon k, or then we can say then it has epsilon k minus 1, or let me think how we can express that. Let's see. If we go back, then we have phi 1 epsilon 1 plus epsilon 2. If we have t equal to 1, then we just have epsilon, that is not a problem. If we have our main information set is t equal to 2, this expression, and we have t equal to 3, this expression. So if we see this t term, this exponent term, it keeps falling, and this subscript for the epsilon term, it keeps rising, right? So we can either go in this direction or we can go in this direction. So since we are following this series, since we are going in this direction for this part of the expression as well, since we followed in this direction, let's try that first, and if that doesn't work, we are going to work in the reverse direction. So if we move in this direction, then the order for this subscript of epsilon will have to keep increasing, but the power for phi 1, the power for this phi 1 will have to fall, right? So there are two ways of writing that. We can either write this as phi 1, so we can start with phi 1, and if it's t equal to 3, it starts from 2, so that means the power will start 1 period lag, so phi 1 k minus 1, and then we have epsilon 1. See, the highest power always belongs to epsilon 1. Here you just have phi 1 and it belongs to phi 1, epsilon 1. So epsilon 1 always has the coefficient with the highest power, because phi 1 here is 0, phi 1 to the power 0. So epsilon 1 has phi 1 to the power 1 and epsilon 2 has phi 1 to the power 0. Similarly here, epsilon 1 has phi 1 square, the highest. Then you have epsilon 2 which has phi 1 and epsilon 3 which has phi 1 to the power 0. That is nothing. So the highest power belongs to epsilon 1. Then you have one exponent false, so you have k minus 2 and then epsilon 2 becomes, so that is this part. Then it goes to phi 1, then again k falls, the exponent falls, and you have epsilon 3, and it goes on like this, right? The last term, see, if this is t equal to 3, the last term is epsilon 3. If this term is t equal to 2, the last term is epsilon 2, which means the last term here will be epsilon k, right? This is one way of expressing the third term. Now what we can do is, we can shorten this, right? So we have to shorten this. Let me just change the color of this highlight to, let's say, a light green. So we have to shorten this expression. It's too big an expression, so we want to shorten this. So yk, it's already one letter, we can't shorten that further. Phi naught. So this looks like a series, like it looks like an AP series. It's a GP series, sorry. So 1 plus phi 1 plus phi 1 to the power 2 plus phi 1 to the power 3, that's a very common series, and we all know that if we want to shorten it, we can do so. If we want to put 1 minus phi 1 to the power k by 1 minus phi 1, right? I think I have a video on GP series and I'm going to be trying my best to find it. I'm going to link it somewhere in the description box below or even in the top right corner of the video, but that is the expression for this series. Then we are going to keep the phi 1 k y naught term. We can't shorten it any further, so let me just highlight this portion. So this blue highlight becomes this. You have this yellow highlight which is here. So the first two terms are over, and then we have to work with this. Now, as I said before, there are two ways of writing this. You can either go in this direction or you can go in this direction as well. What do I mean by that? We're going to start with the opposite direction. So if we start in this direction, then the power of the exponent of epsilon phi 1 keeps rising. If we look in this direction, then the power of phi 1 keeps rising, and the subscript of epsilon keeps falling. So we are going to try and make use of that, and we're going to see. So this is a summation, right? We can use a summation notation, and I'm going to be putting the subscripts and superscripts later. Let's see if we can move in this direction. So if we move in this direction, we have a phi 1 here, of course. Or do we? Yes, of course, we have a phi 1 here. And as I said, the power keeps increasing. So if the power keeps increasing, this summation progresses on the basis of I. So you have some I and it starts from some value and it ends with some other value. So I'm not going to be putting that value right now. Let's suppose I just put an I. So this phi 1 is going to be starting at I. And then as I increases, this power will keep increasing. I always increases in summation, so the power will keep increasing. And then this thing will have to fall. Now let's see how we can adjust that. So if phi 1 starts at I and the first term has to be phi 1 to the power, so phi 1 to the power 0 has to be the least value, right? This gives you phi 0. There's also a phi 0 involved here. There's also a phi 0. Where is the phi 0 in the previous step? Yes, there's a phi 0 involved here as well. So if you want the minimum to be phi 0 and the first exponent is I, then I has to start from 0. Phi 1's first exponent is 0. Phi 1's minimum exponent is 0. You have a phi 1 to the power 0 here. You have a phi 1 to the power 0 here. You have a phi 1 to the power 0 here. The minimum value for phi 1 to the power something is 0. And the minimum that you can find from this summation term is I. So you have to start from I equal to 0, right? So that means you have this value. Now let's think about the epsilon term. Epsilon. This starts from k, right? There has to be a k involved. Now the term associated with phi 1 to the power 0 is epsilon k. So now if I increases, this subscript has to fall. So you have to put some minus I something along that. Now let us check. If I increases, this k minus I falls. So if I increases along this direction, the k value, k, then k minus 1, and it will keep falling. So this part is consistent. Now let's check for I equal to 0. Do we get this term? Yes, we do. Phi 1 to the power 0 epsilon k. So this term actually encapsulates this entire green equation. And this will have to end at, so this is the last term, right? K minus 1. So you can see that if we start from here, the first term is this and the last term is this. So this will be the highest value of I. Compare with this will be the highest value of I. So you have to put k minus 1 over here. See, if you put k minus 1 over here, then k minus 1, think of this term. If you put I as k minus 1, right, this I keeps changing. So k minus, and then you put the highest value of I is k minus 1. So that's 1. See, epsilon's subscript becomes 1. So this entire expression is consistent. You can do a double check like this and you can find out that this is the final expression for let me just change that color here. This is the final expression for the iterative method that is applied on the AR1 series. This generates a different story and we are going to be finding out what actually it tells us. And this is actually a very important expression for the AR1 series. It's of course very different from the AR1 series that we discussed way back here, and it reveals a different story, and we are going to be discussing about it in our next video.